This video serves as the culminating lecture for Math 333 Ordinary Differential Equations at Western Illinois University. And we are going to finish section 7.2, Transformations of Initial Value Problems using Laplace Transformations. So in 7.1, we already discussed how to compute Laplace transformations, how to find the inverse transforms of various functions. And then in 7.2, we introduced how to utilize those Laplace transforms in order to solve initial value problems. We, in a previous video, discussed this flow chart where we take a differential equation in x of t, we apply the Laplace transformation. It results in an algebraic equation involving x of s, which is the Laplace transform of lowercase x of t. We solve algebraically for that function x of s. And then once we have solved for x of s, we want to apply the inverse transform to get back to our solution. And I emphasized in that video that this process takes into consideration the initial conditions on your initial value problem as you apply the Laplace transform in what I labeled as step 2. So there's no additional work once you've done the inverse transform to, for example, solve for any constants. That has already taken place in the process of the problem. So in this part 2 video, I want to focus on finding inverse transforms of various functions. And so in order to do that, we're going to introduce theorem 7.2.2 first. And it says the following. Assuming that you have a function that is piecewise continuous and satisfies the conditions of exponential order, which is what we were requiring in the previous video in order to use transforms to solve IVPs, then the result says the following. If we would like to take the transform of the integral from 0 to t of some function f of tau d tau, then we can slip that Laplace transform into the integral, but we have to pay for it with this factor of 1 over s out top. And notice that this variable here in the upper limit of integration is what is then imposed in our f of t function. And so while this is one way to state the theorem, what's more commonly used is this second rendition. So we can write it in a different way in terms of the inverse transform by saying that if we want to find the inverse transform of f of s over s. So here we have this extra factor of s on the denominator. Then what we can do is we can lower the degree of the denominator by 1, in other words, drop that factor of s, but we pay for it with this integral in front. And so rather than having to take something that might be rather significant with separation by partial fractions, we can say, all right, if we have an extra factor of s, that's fine. We can take care of it, but it requires introducing a integral. Now here again, the one thing that I want to emphasize is tau. Make sure that you're rewriting your inverse transform in terms of tau and not t. And then we'll get back to t here once we apply the integral and evaluate using the fundamental theorem of calculus. So the remainder of these notes is just practicing using this theorem in order to find inverse transforms. So we have apply theorem 2 to find the inverse Laplace transform of the function. All right, so what we see here is this extra factor of s on bottom. We would like to find the inverse transform of this expression. And so according to the theorem, I can write this as the integral from 0 to t of the inverse transform of 3 over, I drop a factor of s in the denominator, so it just becomes s plus 5. And again, remember that this is in terms of d tau. Now I can use linearity of the inverse Laplace transform to factor out that constant 3. And then just so that it looks the way the formula is in the table, I'm going to write this as an s minus a negative 5. All right, so I don't expect you to have all of these inverse transforms memorized, and I will most certainly provide this table on any exams that you would need. So I'm going to scroll up to page 2, and we're looking for the inverse transform of 1 over s minus some a value. So let's scroll on up. Okay, and so we see this in the bottom of the first column here, 1 over s minus a. Its inverse transform is e to the at. So we're going to have an e to the negative 5t. But again, remember, we want it in terms of tau, not t. So let's come back down to ours. I'm going to recopy the integral, keep my coefficient, and then what I have here is an e to the negative 5, again, using tau rather than t. So now let's carry out this integral in terms of tau. If I did a U-substitution, it would kick out a negative 1/5. So I get negative 3/5 e to the negative 5 tau. And this is going to be evaluated from 0 to t. So I'm going to keep my negative 3/5 out front, and I get e to the negative 5t minus 1, since e to the 0 is 1. And so this is the inverse transform of 3 over s times the quantity s plus 5. All right, so we could have done this directly, but what we would have had to have done, and let me grab a different color here, if we wanted to find this directly without integration, we would have had to split this up with partial fractions. And while it's not the end of the world, it just adds some extra algebra in here. And so this theorem allows us to bypass partial fraction decomposition, and instead it just swaps it for integration. So let's do a few more examples here. Let's look at problem 20. Same approach here. We want to find the inverse transform using the given theorem. So our goal is to compute the inverse transform of 2s plus 1 over s times s squared plus 9. Okay, and so here is this extra factor of s that we see in the denominator. We would like to omit that, so we will drop that and pay for it with an integral. So now we're finding the inverse transform of 2s plus 1 over s squared plus 9 d tau. And so what I'm going to do is I'm going to split this up, and I'm going to write them in a way that it's going to be easy to find the transform. So I have 2 times s over s squared plus 9 plus 1 over s squared plus 9. And we know what this function is, s over s squared plus k squared. Let's go ahead and take a look up. S over s squared plus k squared. All right, so you see it highlighted in green there. That is the cosine kt function for k equal 3. Now, the other one with an s squared plus k squared is sine of kt, but notice that we need this k up top, and we're missing that currently. So our k value is 3. So let's go ahead and introduce that into our fraction. So I'm just going to add in here a 3 over 3. And now let me write this out once more using the linearity property. This is 2 times the inverse transform of s over s squared plus 9 plus 1/3 times the inverse transform of 3 over s squared plus 9. And all of this, of course, is with respect to tau. So now we can do the inverse transform. We have 2 cosine of 3 tau plus 1/3 sine of 3 tau d tau. All right, so now we're able to go ahead and integrate. A U-substitution will kick out a 1/3 in both cases. And so I get a 2/3 sine of 3 tau minus 1/9 cosine of 3 tau. And I want to evaluate from 0 to t. The sine function is going to die at 0, but the cosine will not. And so in the end, I get 2/3 sine 3t minus 1/9 cosine 3t. And then I'll get minus a negative 1/9 there for cosine. So that's a positive 1/9. All right, and there's our inverse transform. Last but not least, we have problem 22. So let's take a look at that one. As always, we're using this theorem to simplify that extra factor of s so as to subvert having to do partial fraction decomposition. So our goal is to compute the inverse transform of this given function. I'm going to drop the s on the denominator and insert my integral. So it becomes 1 over s squared minus 9 d tau. And similar to the last example, I just need to stick a 3 over 3 in here. And so I will rewrite this as the integral from 0 to t of 1/3 inverse transform of 3 over s squared minus 9. So this slightly differs from the example up above because we have s squared minus k squared as opposed to s squared plus k squared. So let's go ahead and scroll back up to our table of common Laplace transforms. And so instead of the sine function, we're looking at hyperbolic sine or sinh. And here again, our k value is going to be 3. So this inverse Laplace transform is going to be sinh of 3t. So I have the integral from 0 to t of 1/3 sinh 3 tau d tau, keeping in mind that our variable of integration is tau here. And then let's go ahead and integrate. If you haven't had a lot of practice with hyperbolic trigonometric functions, that's okay. If you're in one of my courses, I typically won't put these problems on the exam, but I just want to expose you to them in the notes and possibly the homework. So if you need to go and look up the integral or derivative of these hyperbolic functions, that's perfectly fine. Both sinh and cosh, their derivatives don't kick out a negative. So the derivative of cosh is sinh and the derivative of sinh is cosh, and vice versa for the integral. So I am going to pop out a 1/3 from a U-substitution, but I just get the integral is cosh 3 tau, evaluated from 0 to t. And so I get 1/9 cosh of 3t. And then cosh of 0, much like cosine of 0, is 1. So this becomes minus a 1/9. All right, and so here is your inverse transform. This concludes our notes for the semester. Thanks so much for tuning in throughout the semester. And let me know if you get any questions.